Hello everyone. In this lecture, we will study about what is synchronous machine in a step-by-step manner. So we will move on the outline or content of this presentation. First, we will introduce what is synchronous machine. Second, we will move on the construction and the working principle of the synchronous machine. Next, we will move on the classification and types of the different type of synchronous machine. Number 4 is rotational speed or electrical frequency of that machine. Next, we will move on the generated voltage equation as well as the voltage regulation, and we will study about the equivalent circuit of the synchronous machine like synchronous generator as well as the synchronous motor. Next, we will move on phasor diagram for lagging, leading and no load condition. After this, we will study about the determination equivalent circuit parameter of the alternator. Now we will move the next topic, parallel operation of the alternator. Further, we will move the next topic, name is synchronous motor. So in this topic, we study about what is synchronous motor, how it is work. Next is operating principle of the synchronous motor. After this, we study about the vector diagram of synchronous motor, and finally we learn what is the application of the synchronous motor as well as the synchronous generator. So with the introduction of the synchronous machine. So first question occur in our mind, what is the synchronous machine? So its name suggests synchronous means it's a constant speed drive. So synchronous machine is a rotating electrical energy conversion device, means it converts the energy from one form to any other form. Synchronous machine is a doubly excited machine, means its stator winding as well as the rotor winding both are excited by separate source. So synchronous machine is a constant speed drive. So this is called the synchronous machine because the speed of that machine is a constant. So finally, the definition of the synchronous machine is synchronous machine is a doubly excited constant speed energy conversion device which convert one form of the energy like electrical or mechanical to another form like mechanical to electrical. So this is a proper definition of synchronous machine. Next, we will move on the construction and working principle of the synchronous machine. The construction of the synchronous machine. The synchronous machine consists two main parts. First one is called stator, another is called the rotor. So stator is a stationary part of the machine and rotor is the rotating part or movable part of the machine. Synchronous machine consists two winding known as armature winding and field winding. The winding which carry excitation current is called field winding. The winding which carry load current is called the armature winding. Armature winding placed on stator and the field winding placed on the rotor. The synchronous machine operated into two modes, generating mode and motoring mode. So firstly, we will understand what is the generator and what is the motor. Generator is a device which convert mechanical energy into electrical energy. Motor is a device which convert electrical energy into mechanical energy. So in a synchronous generator, a DC current is applied to the rotor winding, producing a rotor magnetic field. The rotor is then turned by external means, producing a rotating magnetic field, which induces a three-phase voltage within the stator winding. In a synchronous motor, a three-phase set of stator current producing a rotating magnetic field, causing the rotor magnetic field to align with it. The rotor magnetic field is produced by DC current applied to the rotor winding. The field winding are the winding producing the main magnetic field, or the winding which carry the excitation current, means the supply is connected. The rotor winding for synchronous machine means field winding placed on a rotor circuit. Armature winding are the winding where the main voltage is induced, placed on stator. The rotor of the synchronous machine is a large electromagnet. The magnetic poles can be either salient or non-salient. In this figure, you can see the diagram of non-salient pole rotor. Usually 2 and 4 poles rotor. Rotor are made laminated to reduce the eddy current losses. And second figure, you can see the salient pole type construction. Salient means projected rotor poles. You can see the pole of the rotor is projected, so it is called the salient pole construction. Non-salient pole construction is also called a round rotor or the cylindrical rotor construction. So next question occurs in our mind: how can we supply the DC to the rotor? The common approach are used to supply the DC current to the field circuit or the rotating rotor. Number 1, supply the DC power from an external DC source to the rotor by means of slip ring and brushes. Number 2, supply the DC power from a special DC power source mounted directly on the shaft of the machine. Slip ring are metal rings completely encircling the shaft of a machine but insulated from it. One end of the DC rotor binding is connected to each of the 2 slip rings on the machine shaft. Graphite-like carbon brushes connected to the DC terminal right on each slip ring supply DC voltage to field winding regardless the position or the speed of the rotor. So you can see the diagram. In this figure, brushes and slip ring are clearly shown. Brushes are made by the carbon because the current conducting capacity of the carbon is very high, and slip ring are made by the metal. Slip ring and brushes have certain disadvantage: increase the friction and wears, therefore need maintenance. Brush voltage drop can induce significant power losses. Still, this approach is used most of small synchronous machine. Means this approach we can't use for the large size of the synchronous generator as well as the motor. On the large generator and motor, brushless excitation are used. A brushless exciter is a small AC generator whose field circuit are mounted on the stator and armature circuit are mounted on the rotor shaft. The exciter generator 3-phase output is rectified to the DC by a 3-phase rectifier and feed into the main DC field circuit. It is possible to adjust the field current on the main machine by controlling the small DC fields current of the exciter generator. Since no mechanical contact occurs between the rotor and stator, exciter of this type require much less maintenance. Brushless excitation is suitable for the large size of the generator. Because if we use brushless excitation, so we reduce the sparking as well as the power losses in a synchronous machine. Next is a working principle behind the synchronous machine. So synchronous machine work on the Faraday law of electromagnetic induction principle, or it is work on the interaction between the static magnetic field to the rotating magnetic field. In armature circuit, we provide a three-phase AC supply which create a rotating magnetic field. In a field circuit or field winding placed on the rotor, excited by separate DC source, DC supply create the static magnetic field. So the interaction between these two fields, static magnetic field and rotating magnetic field, provide the rotation of the motor. If the stator rotating magnetic field is synchronized with the rotor field, so machine is called the synchronous machine. Field winding is excited by separate DC source to create the static magnetic field, and armature winding is excited by the AC source to create a rotating magnetic field. When the static magnetic field and rotating magnetic field synchronize, so the machine is called the synchronous machine. Next, the operation principle of the synchronous machine, a step-by-step manner. Firstly, the rotor of the generator is driven by the prime mover. After this, a DC current is flowing in the rotor winding which produce a rotating magnetic field within the machine. Next, the rotating magnetic field induced a three-phase voltage in the stator winding of the generator. So this is a simple flow chart for the operating principle of the synchronous machine, or we can say that the synchronous generator. So we'll move on next topic, the classification and the type of the synchronous machine. Synchronous machines are broadly classified into two categories on the basis of the rotor construction. Number one is a salient pole synchronous machine, and second is non-salient or cylindrical or round rotor synchronous machine. In a salient pole type construction, what is the meaning of salient pole? The meaning of salient pole is projected rotor poles. Non-salient means the rotor poles does not projected. The rotor poles is in the cylindrical form or round rotor form is called the non-salient pole type construction. So there is two classification of synchronous machine, salient pole construction and non-salient pole construction. Now the salient pole synchronous generator are used to hydraulic turbine, have to run at low speed. You can see the diagram. In a salient pole construction, the air gap between the stator and rotor is non-uniform. because along the pole the air gap is different and between the pole the air gap is different. So non-uniform air gap provide two reactants: direct axis reactance XD and quadrature axis reactance XQ. A large number of the poles are required on the rotor. If we made or choose the salient pole construction, so required a large number of poles. The salient pole synchronous generator are used in hydroelectric power plant. This is the diagram of salient pole synchronous generator, stator diagram as well as the rotor diagram. You can see the rotor pole is salient or projected. So the name is salient pole synchronous generator. Non-salient pole synchronous generator. The non-salient pole synchronous generator or cylindrical rotor synchronous generator. In this generator, the air gap is uniform between the stator and rotor. The speed of non-salient pole synchronous generator is higher. So it is used for steam power plants. The rating of this kind of synchronous generator up to 2000 MVA. You can see the diagram of the turbo generator. Turbo generator are used in a steam power plant because the steam power plant the speed of the turbine is higher compared to hydropower plant. So the main difference between the salient and non-salient pole type machine: in a salient pole type machine, the speed is low, air gap between stator and rotor is non-uniform, so create the two reactants, direct axis reactance and quadrature axis reactance. In a cylindrical rotor synchronous machine, air gap is uniform, so it can be used for the high speed turbo generator. Now the diagram of the non-salient pole synchronous generator, stator diagram as well as the rotor diagram. Now we will move the next topic, rotational speed or electrical frequency of synchronous generator. By the definition, synchronous generator produce electricity whose frequency is synchronized with the mechanical rotational speed. So the electrical frequency Fe is equal to Nm into P divided by 120, where Fe is the electrical frequency in Hertz, Nm is mechanical speed of the magnetic field or rotor speed for synchronous machine in RPM, and P is the number of poles. The steam turbine are the most efficient when the rotor rotating at a high speed. Therefore, to generate 60 Hz, they are usually rotating at 3600 RPM and turn two-pole generator. Water turbine are the most efficient when rotating at low speed, 200 to 300 RPM. Therefore, they usually turn generator with the many poles. Now we move the next topic, generated voltage in synchronous. The generated voltage of the synchronous generator is given by E is equal to Kc phi into Fe, where phi is equal to flux in the machine, Fe is equal to electrical frequency, and Kc is equal to synchronous machine constant. You can see the saturation characteristics of the synchronous generator. This characteristics plot between the generated voltage and the field current. In a horizontal axis, we consider a field current IF, and a vertical axis we consider a generated voltage. Next topic is voltage regulation of the synchronous generator. A convenient way to compare the voltage behavior of two generators is by their voltage regulation. The voltage regulation of the synchronous generator at a given load power factor and at rated speed is defined as voltage regulation is equal to no load voltage minus of full load voltage divided by full load voltage into 100%. We always calculated voltage regulation in a percentage form. So the formula is VR voltage regulation is equal to E NL means no load voltage minus of VFL means full load voltage divided by VFL means full load voltage. So where VFL is the full load voltage and ENL is no load terminal voltage at the rated speed when the load is removed without changing the field current. For a lagging power factor, the voltage regulation is fairly positive. For a unity power factor, voltage regulation is small positive, and for a leading power factor, the voltage regulation is negative. Now move on. The next topic is equivalent circuit of the synchronous machine. First question is that why we make the equivalent circuit and why we study the equivalent circuit. So by using this, we can find out the parameters like the total reactance, total resistance of the machine. Move on the equivalent circuit. The internal voltage EF produced in a machine is not usually the voltage that appear at the terminal of the generator. The only time EF is the same as the output voltage of a phase when there is no armature current flowing in the machine. There are a number of factors that cause the difference between EF and VT. Induced voltage is called EF and VT is called the terminal voltage. So the distortion of the air gap magnetic field by the current flowing in the stator called the armature reaction. The self-inductance of the armature coil, the resistance of the armature coil, and the effect of salient pole rotor shapes. So this is the equivalent circuit of cylindrical rotor synchronous generator where EF is called the induced voltage or supply voltage in this diagram and VT is called the terminal voltage. X represent the reactance of the circuit and RA is called the armature resistance. IA is known as the armature current. So this is the equivalent circuit of cylindrical rotor synchronous generator. Next topic is a phasor diagram of the synchronous machine. So this is the phasor diagram for cylindrical rotor synchronous generator in case of lagging power factor condition. We can draw the phasor diagram for three conditions: lagging power factor condition, leading power factor condition, and unity power factor condition. So in a lagging power factor, the terminal voltage is less than to the induced voltage. This condition, machine is overexcited condition. Leading power factor, in this condition, the Vt is greater than to EF. For this, machine act as a under-excited condition. Third one is if Vt is equal to EF, so machine act as a normal excitation. Next, the determination of equivalent circuit parameter. The equivalent circuit of the synchronous generator that has been derived contains three quantities that must be determined in order to completely describe the behavior of the real synchronous generator. The saturation characteristics, relationship between IF and F, and therefore between of IF and EF, means field current and field voltage. The second is the synchronous reactance axis. Third one is the armature resistance RA. The above three quantity could be determined by performing the following three tests: by using open circuit test, short circuit test, and DC test. So discuss about the open circuit test. In open circuit test, the field winding is connected to the DC source and the armature winding is open circuited. The generator is turned at the rated speed. The terminals are disconnected from all the loads and the field current is set to 0. Then the field current is gradually increased in steps and the terminal voltage is measured at each step along the way. It is thus possible to obtain an open circuit characteristics of a generator. Plot between Vt versus IF. Short circuit test. In this test, the field winding is connected to the separate DC source or excited by the separate DC source, and armature winding is short circuited by using a wire. Adjust the field current to 0 and short circuit the terminals of the generator through a set of ammeters. Record the armature current ISC as the field current is increased. Such a plot is called the short circuit characteristics. So in a diagram, you can see the OCC is called open circuit characteristics. SCC is called the short circuit characteristics. Short circuit ratio, in short SCR. Another parameter to describe synchronous generator is the short circuit parameter. The short circuit of the generator defined as the ratio of the field current required for the rated voltage at open circuit to the field current required for the rated armature current as short circuit. SCR is just the reciprocal of the per unit value of saturated synchronous reactance calculated by SCR is equal to IF in V rated and IF divided by IF in I scattered. Or we can say that SCR is equal to 1 upon XS in per unit. The next is the parallel operation of the synchronous generator. So why we need a parallel operation? Most of the synchronous generators are operating in parallel with the other synchronous generator to supply power to the same power system. Obvious advantage of this arrangement are several generators can supply a bigger load. Number 2, a failure of a single generator does not result in a total power loss to the load, increasing reliability of the power system. Individual generators may be removed from the power system for the maintenance without shutting down the load. A single generator not operating at near full load might be quite insufficient. While having several generators in parallel, it is possible to turn off some of them when the operating the rest of the need full load condition. So the condition required for the parallel operation of the generator. A diagram shows the generator. Two generators will be connected in parallel. When the switch S1 is closed, however, closing the switch at arbitrary movement can severely damage both generators. If voltage are not exactly the same in both lines, that is A and A dash and B and B dash, a very large current will flow when the switch is closed. Therefore, to avoid this, the voltage coming from both the generator must be exactly the same. Therefore, the following condition must be met for the parallel operation of the two alternator or synchronous generator. Number 1, the RMS voltage of the two generators must be equal. The two generators must have the same phase sequence. What is phase sequence? So R by B is called the phase sequence. The phase angle of two phases must be equal. Number 4, the frequency of oncoming generator must be slightly higher than the frequency of the running system. Next topic is a synchronous motor. So synchronous motor is a rotating electrical device which convert electrical energy into mechanical energy. A synchronous motor is the same physical machine as a generator, except that the direction of real power flow is reversed. Synchronous motors are used to convert the electrical power into mechanical power. Most synchronous motors are rated between the 150 kW and 15 MW and turn at the speed ranging from 150 to 1800 revolution per minute. Consequently, these machines are used in heavy industry. At the other end of the power spectrum, we find tiny single-phase synchronous motor used in control device and electrical clocks. Next is the operating principle of synchronous. The field current of the synchronous motor produces a steady-state magnetic field. So the three-phase set of voltage is applied to the stator winding of the motor and which produce a three-phase current flow in the winding. This three-phase set of the current in the armature winding produce a uniform rotating magnetic field. Therefore, there are two magnetic fields present in the machine, and the rotor field will be turned to the line up with the stator field, just as two bar magnet will tend to line up if placed near each other. Since the stator magnetic field is rotating, the rotor magnetic field and the rotor itself will try to catch up. The larger the angle between the two magnetic fields, the greater the torque of the rotor of the machine. Next is a vector diagram of the equivalent circuit of the synchronous motor is exactly same as the equivalent circuit of the synchronous generator, except that the reference direction of the armature current IA is reversed. The basic difference between motor and generator operating in a synchronous machine can be seen either in the magnetic field diagrams or in the Phasor diagram. In a generator, EF lies ahead of VT and BR lies ahead of BNet. In a motor, EF lie behind VT and BR line behind BNet. In a motor, the induced torque is in the direction of the motion, and in a generator, the induced torque is the counter torque opposing the direction of the motion. So you can see the vector diagrams for synchronous motor. We consider Vt into horizontal axis, current Ia placed leading to the voltage Vt by angle theta. After this we can draw the losses Ia into Xs or Ia into Ra. So we get the finally induced EMF EF, and the angle delta is called the load angle. So this is the phasor diagram for leading power factor or overexcited condition. In this condition, Vt is less than 2 EF, and the corresponding magnetic field diagram of the synchronous motor. Next, second diagram is the phasor diagram of underexcited synchronous motor, means lagging power factor. In this diagram, we can see that Vt is greater than 2 EF. So now we will move the applications of the synchronous motor as well as the synchronous generator. Synchronous motors are usually used in the large size because in a small size they are costlier as compared with the induction machine. The principal advantage of using synchronous machine are as following. The power factor of the synchronous machine can be controlled very easily by controlling the field current. It has very high operating efficiency and constant speed. For operating speed less than about the 500 rpm and high power requirement above 600 kilowatt, synchronous motor is cheaper than the induction motor. In view of these advantages, synchronous motors are preferred for driving the load requiring high power at low speed. Example, reciprocating pumps and compressor, crusher, rolling mill, grinder, etc. So this is the application of synchronous motor, and the synchronous generator, or called as alternator, is used in a power plant to generate the electrical energy. So this is a short presentation related to synchronous machine. This is the references. So thank you for watching the video.